Okay, we're gonna try to solve a pretty classic physics problem here today, and the problem goes something like this. Imagine, if my pen works here, imagine you have a small sphere of some sort, maybe like a perfectly round marble, and you set it on top of like a dome or a hemisphere of some sort, right? So some large sphere like this. Having some technical difficulties here. Okay, there we go. And you put up on the top here and you let it roll down. Okay, so you're going to release it. It's going to roll, say, in this direction. If it starts at a velocity of 0, at what point down the side of this larger sphere or circle will it actually leave the surface? Okay, I've heard it where it's like an ice ball with no friction, but I like, let's say it's a marble sitting on top of a perfect globe. Okay, when will it leave the surface? All right, let's see how we're going to think about this problem. Okay, we're going to fire a equator around it. Okay, and we'll throw this in here. And for now, we will just call this a unit circle. Okay, so let's imagine then at some time in the future, this ball, and I just picked the ball, please. Okay, will end up down here somewhere, right? And at some point we can imagine it's going to pop off the surface, okay? And we've called this a unit circle just to make the math a little bit more easy to deal with, okay? So let's think about how this is going to work. So essentially, when will this come off the surface? Well, it should come off the surface when the normal force between this sphere and the large dome reaches 0, drops to 0, okay? So let's think about it when it's still at the top. What are our forces, or what's our force pair going to look like there? So we've got a gravitational force pointing down, like that. And we have an equal and opposite normal force, oh, for goodness sake, pointing up here. Okay, so you got your, what's going on here? You got your FG pointing down. I think I can do this. There we go. And you have your normal force pointing up. So at the beginning, Fg is equal to the normal force. And we know this will come off the surface, right? Essentially when the normal force drops to 0, at that point they're no longer in contact. If this thing had no velocity whatsoever, all right, it would, at each instant, if it had no velocity, if I just started it at this point, right, there would be some normal force until I got to the 90-degree point. At 90 degrees, I know I'm going to have no normal force, okay? However, as this increases in its velocity, right, at a certain point, gravity will not be able to keep it on this arc anymore, all right, and it will leave. And it will leave somewhere before the 90, okay? If it had 0 velocity, it would kind of stay in contact till 90, and then no more normal force would be possible. That's not exactly what's happening with this problem. So let's examine it at some point here and see what the forces are going to look like over here. So you're still going to have your Fg force, right, running down. But now this is going to behave more like a inclined plane problem. So let's imagine you have an inclined plane that looks like that. Let's imagine this object is just sitting on the inclined plane here. And I realize that's not exactly what's going on. Let's imagine it's sitting on the inclined plane like that. All right. So what component of this then is going to be providing the centripetal force at this point? We got Fg down. What is providing the centripetal force? Remember, centripetal force always has a point towards the center. So here it's easy, right? Gravity is doing it. But here, gravity's pointing in this direction, and the center of the circle is over here. So there's got to be a component pointing along, and we'll call this R, pointing along R, the radius, and aiming at the center of the circle. So we can actually go ahead and draw that in, and we'll make a comparison to it and the normal force at that point in time. So there's got to be some component of gravity pointing down there, okay? And there's some component here. So there's a component of gravity pulling towards the center. And that should be equal but opposite in direction to the normal force, shouldn't it? Right? The normal force is perpendicular to this quote-unquote surface, which is really just a tangent line at that given instant. And then there's some component of gravity that's going to still be pointing towards the center. Okay? So I guess what we could do then is we could probably write it like this, and we could say that we're interested at the point where the centripetal force plus the normal force drop to 0. Or I guess in another way of saying it, where the normal force is equal to and opposite the centripetal force. All right, so let's maybe throw in some information here. So we know that this down here is Fg, okay? If, now this is not 90, sorry, this is some value, we're just going to call it theta. Theta is the angle that we're currently at. And of course, due to interior angles, and these are two parallel lines, this will also be theta, okay? So we know that Fg is equal to mg. And then we know that the centripetal force, or if you want actually the normal force, at this point will be equal to mg times the cosine of theta, right? Mg cos theta, right there. I'll actually come in here and put that in. Mg cos theta is going to be equal to Fc. And velocity is obviously going to play a role here too, right? And we know that Fc is equal to mv squared over r. We've learned that in the past. We've derived that out in the past. So then we can plug that in. Now we're looking at this situation. Okay, so the question is, how do we find the velocity at that given point in time? How do you find the velocity at that given point in time? So what you're going to do is you're going to base it on your concepts from energy. Okay, you're going to do it with energy equations. So remember, we're on a friction-free surface, all right? Okay, so if that's true, then the velocity is going to be based on the gravitational potential energy being converted into kinetic energy. Okay, so we're going to call this H. We don't want it dotted. It's like apparently the first time I've ever done one of these. Okay, so there's H. So we can then say that EK is being converted into EG. Seeing as how there's no frictional losses, we can then say this: 1/2 mv squared, that's kinetic energy, is coming from mgh. Now, how do we define height? Well, height is going to be based on 1, right? The whole r is 1, r equals 1. 1 subtract r times the cosine of theta, right? It's the adjacent angle. So h equals r, 1 minus r cos theta. So let's just go back to here and change around what we can. So mass comes out of there, and we get that v squared is equal to 2 times gh, and then h, the height, is going to be equal to 1 minus r cos theta. Like that. And just to clarify, r cos theta is this right here. R cos, it's hard to write sideways, theta. Right, so there's your r cos theta. Since all of r is equal to 1, height for your mgh, right, this is your mgh here, height from the top to your current position is 1 minus r cos theta, or 1 minus 1 times cos theta. Since that's just going to be a 1, we'll end up with this. Right? There's a 1 in front of there, but we can just, like, if r equals 1, because we're on a unit circle, we can actually just get rid of r. All right, so now we have an expression for the square of v. So mass crosses off over here. We've now got g cos theta equals v squared over r, where v squared is going to be equal to this, 2g 1 minus cos theta all over r. Okay, so I subbed in for v squared this value. So here's my v squared for my centripetal force formula. Now, let's see what we can do with this. So g cos theta equals, that is now this. Let's distribute this in. So we get 2g minus 2g cos theta all over r. But remember, r is 1, right? So sub in 1. And then you get this. G cos theta equals 2g minus 2g cos theta. What do you notice in each of those expressions? So you can get rid of g from each one of them, right? You can divide g off both sides. Now we're almost there. We've got now cos theta equals 2. Oops, no it doesn't. Cos theta equals 2 minus 2 cos theta. Or, add it on there, we get 3 cos theta equals 2. Or cos theta equals 2/3. Or theta equals the inverse of 2/3. And you will find that that is exactly the correct answer, and it works to be like 48 degrees. So your magic number is 48.189 yada yada. Or let's just call it 48.2 degrees. Does radius appear here? If radius does not appear here, radius is irrelevant. So allegedly, radius is always going to be an irrelevant scenario here. And you know what? That kind of makes sense intuitively, I think, right? The radius is smaller, it's going to reach velocity sooner, right? The angle that it's at, or the curve, the slope is higher, so the acceleration will therefore be higher. If you made this, an extremely large circle, it would eventually get to that velocity, it would just take a lot longer. So it turns out, yes, there's a universal angle where this guy theoretically pops off the surface. It's always at 48.2 degrees, or cos 2/3, inverse cos 2/3.